Our final talk of this session is called Quick and Accurate Attack Detection in Recommender Systems through User Attributes. Mehmet, Aktukmak.
Hello, my name is Mehmet. I'm a PhD student at University of South Florida. I'm happy to present my short paper, which is related to attack detection in recommender systems. Most of the commercial platforms use recommender systems to improve their user satisfactory and profit. Most of these systems use data-driven machine learning models, and the main source of these models is mostly user feedbacks. And however, it's likely that some malicious activities can be performed by injecting fake profiles. For this type of attacks, the main motivation can be, especially for e-commerce platforms, can be to promote an item to increase its sales, or to mute an item, a rival item, or just the attacks can be performed to reduce the efficiency of the platform by disturbing it. In the last 2 decades, the attack detection has been an active research field, and many attack types have been proposed, and many attack detection algorithms have been developed to mitigate this type of attacks. In general, an unsupervised attack detection algorithm can follow the following procedure. We have ratings of genuine users in the system, registered in the system, and we employ a feature extraction model to find some features that are useful for attack detection. So in the offline phase, in the online phase, for the new users, for the test users, we also use the ratings of them and use the same feature extraction model, and we compare features and to make a decision. However, most of the platforms require from the users to put some attributes. In this framework, we aim to exploit these user attributes as additional information to improve attack detection performance. In regarding to this motivation, we can have following research questions. Most of the user attributes, we can say that they are mixed data type, which is including clear valued and categorical valued attributes. So regarding to this issue, how can we exploit these mixed data type user attributes to improve attack detection? And since we have multiple data, how can we extract features that can represent jointly both ratings and user attributes, mixed data type user attributes? In this framework, we also assume that the attacks are being performed sequentially, which means the attacker performs the attack in short time period. We call it this type of attack as persistent attack. And our last question is how to detect this type of attacks. In this study, we have the following assumptions. The attackers do not have access to user attributes registered in the system. So they put random attributes if they are asked. And to get quick and efficient results, they perform the attack profile injection in short time period. By our proposed framework, we expect to reduce the false alarm rates of individual profile detection, and we also aim to detect system-wide attacks to the platform. Let's say we have some genuine users registered in the system. They have rating history We also have mixed data type user attributes such as occupation, age, gender. We are using a latent arrival model to project user information to a latent space. We train this model by using only the new users. In the test phase, we have new users, so we are using the information of these new users and the trained model parameters to project these new users to a latent space. Then we produce some statistics from the latent space and use it inside a sequential framework. In this framework, we use some like to detect system-wide faults. To project the users to a latent space, we use a latent variable model. For each user, we assign a latent variable which has prior 0 mean false spectral prior. It is the same for latent item variables. And for the ratings, we use dot product false conditional distribution. This part is the same with probabilistic factorization models. Additionally, we model the user attributes linearly. For each real-valued user attributes, we have a linear Gauss model and with parameter Wm, and for each categorical valued user attributes n, we have a softmax, linear softmax model with parameter hn. So the conditional probabilities and priors define the model and the model parameters as well. So we are optimizing this model by using the observations, the ratings, and the user attributes. In this work, we use variational EM algorithm, expectation maximization algorithm, to learn to optimize the model. For categorical attributes, for the likelihoods of categorical likelihoods, we use a quadratic lower bound to make the blockchain probability of the model fully quadratic. We chose bounding bound, which is a fixed curvature lower bound to the log sum expression in categorical likelihoods. Then we infer the variation distribution of the user-related variables. We also do the same for the item-related variables. So for the covariance of the distribution and for the view of the distribution, we follow the general procedure of inferring Gauss linear systems, which is like collected linear and quadratic terms to find the covariance and meanings. In the M step, we optimize model parameters W and H by using their maximum likelihood estimations. For the real valued user attribute, we have W and sigma x n, which is noise covariance on user real valued attribute. Actually, these equations are same with factor analysis models. For the categorical value side, the equations change a bit because of the applied bound. So for sequential attack detection, we first infer the variational distribution by conditioning on trained model parameters and the user attributes. Then we evaluate a latent likelihood for each observed rating. And we compute anomaly score, which is average negative likelihood. This is offline phase, and this is for all genuine users in the system. And in the online phase, for each test user, we repeat the same 3 steps. And additionally, we compute a tail probability, which is simply a fraction of genuine users who has highest anomaly score, then we compute anomaly statistic with alpha significance model. And we decide to create anomaly statistic. And if this statistic is higher than H, we flag a system-wide IR. To show the performance improvement, we use the LATENT dataset. LATENT dataset has 1,000 users with this data type attributes, age, region, and gender. To generate the attack, we picked most popular but simple 3 attack types, random, average, and failing. The attack size is 10%, and for the ratings, the size is 5%. For the attributes of each attack profile, we then vary it from genuine users to make. And we hold out some genuine users and compare with the generated attack profiles to form the sequential attack. This is the detected performance. We compare with generalized lightning ratio test, which just uses the ratings, and we show the improvement. And we also compare with some baseline models. These models use ratings to detect individual attack profiles. And we show some improvements because we additionally use user attributes evidence to improve our attack detection performance. In this study, we aim to exploit user attributes to improve single profile detection and system-wide attack detection. And we developed a unified variable model to learn from ratings and user attributes. And we also show some improvement on sequential attack detection. Since our experiments are preliminary, our first focus will be on to extend them by using more sophisticated and different data sets, largely potentially large, and with different concepts. And another straightforward work would be to use non-linear algorithmic methods instead of linear. Thank you for listening. I'm ready to ask you the questions.
Questions?
Thank you for this talk. I'm still trying to puzzle through the high-level picture here, and it seems to me that when you work through all of this, you've found an effective way of identifying data that badly matches the data set in these hidden attributes. But if that's true, I have 2 concerns about it, and maybe you can allay them. One of them is that might also be the most informative data if it's real. If we find out that we have examples of older women who really like, car crashes and explosions, the last thing I want is to discover that those people get knocked out of my data set because they're rare, rather than being there so that they can help each other find content. And the other concern is, in real applications, even if you take the kind of data like MovieLens, if I wanted to do a better job as an attacker, I could go to public sources and figure out which preferences are more likely to correlate with particular demographic profiles and not be random. I might not be accurate, but I could get a lot closer. I'd like your opinion on are those valid concerns, and is there anything we can do about them?
In this work, actually, we assumed, as you said, the attributes are selected randomly. So, actually, in regarding to this assumption, we have evidence. So, because they do not match the rating expectation given the user attributes. So, it can be learned externally. However, it will not exactly match, and it will produce in our framework, it will produce some additional evidence besides the ratings anomaly. So we are trying to sum up the ratings anomaly and user attribute mismatch. So they can be reduced. The ratings anomalies can be reduced by picking some more sophisticated attacks. Also, user attribute anomalies can be reduced by selecting more proper attributes. But in this work, we assumed they are random and they produce evidence. Yeah, we can consider that aspect. Thank you.
Thank you very much, Mehmet.